Okay, so am I audible? Uh, don't know. Just a second. Please give me a few seconds. Um, okay, cool. Okay, so the motive of today's live stream is nothing special, just resolving a few questions which I just picked up randomly from different mathematics exams. It includes regional mathematics Olympiad, the entrances for Indian Statistical Institute, and so on. So I just plugged randomly some few questions, and I actually don't know. Actually, there is no particular common thing in each of the questions. They are just plucked up randomly. So I hope you will like it. So let's start. So this is the first question. So how to solve this? I just a second. Yeah, just copy this question, and now you might ask that why am I using paint? Well, I don't know. I just I just love paint, and that's why I'm doing this. And also paint is built in, so I don't want, actually I don't want to work a lot hard. Okay, cool. So let's start solving. Okay, so this is the first question. This is as far as I remember. So this question says that let me use the red color. Cool. So so how to solve this question? How to solve this question? Just a second. Give me a few seconds. Just give me a few seconds. Okay. So the first question says that we are given a series of real numbers which are actually given in a particular sequence, and we are told that we are given this particular expression, we are given this particular expression, and we need to show that this particular expression has exactly n roots, n real roots. Okay, cool. So what does real roots mean actually? Now if we plot, just a second, if we plot a graph, if we plot a graph, say something like sorry, if we just plot a graph which looks something like this, okay, something like this. So we call these points, these particular points, the roots of the equation, the real roots of the equation. Now why is it called real roots? Well, basically this is because we're getting real values where these are actually real points. So we're getting real values at those points this particular expression will just become 0. By 0 I mean this particular expression will satisfy. Okay, cool. So let's see how we can basically solve this question. So we have that, so we have this expression. So we are given that 0 is less than a1 is less than a2 is less than a3 and less than so on. This actually continues till an. Now we are told that this particular expression a1 over a1 minus x, a1 minus x plus a2 over a2 minus x plus this will continue till an over an minus x. This must be equal to 2015. So instead of writing equal to 2015, we can just write minus 2015. Say that this particular thing is actually a function. So this is actually a function. Now we need to find the roots, the real roots of this particular function. Basically we need to find that at which positions this particular function is. Basically we need to find that at which particular positions f of x is equal to 0. And we are told that there are exactly n real roots. Okay, so we basically don't need to find the roots, but we just need to prove that there exist n real roots of this particular equation. Okay, cool. So what can we do? What can we do? Well, we can clearly see that f of x, the function f of x, is actually not defined at certain positions. This is a second. Is basically not defined at certain positions. Now what are those positions? You can see that if this particular function is given and we plug in x equals to a1, then this particular function will actually be, okay, let me see here. Now if in place of x we just plug in a1, then we can see that this particular function is actually going to infinity, and actually that is not possible. So we can actually see that the left hand limit and the right hand limit of this particular function is not the same, because if we approach a1 from the left hand side, then this will be diverging to positive infinity, whereas if we approach a1 from the right hand side, then we will have the function which is diverging to negative infinity. Hey Shomadhi, how are you? I'm fine. Okay, cool. Now going back to the question, note that if we apply the limit, just a second, if we apply the limit as x approaching a1, thank you so much, you were thank you so much for this support. I actually required this. Thank you so much. Okay, cool. So this is, we are just approaching limit x tends to a1. So we can clearly see that this particular function is actually continuous in the interval a1 to a2. In the interval a1 to a2, there are no point of discontinuity. So we can clearly say that this particular function is continuous in the interval a1 comma a2. Okay, so we will be basically using this idea. So if we approach a1 in the interval a2, obviously we need to approach from the right hand side. So okay, f of x. Now the one thing you can notice, the first term of f of x is a1 over a1 minus x. Now if you approach x from right hand side, if you approach a1 from the right hand side, you can clearly see that this thing is actually this thing is actually a negative number, and we are already told that a1 is positive. Okay, and we know that if x approaches a1, then this entire entity approaches infinity. Now since we have negative here, so it approaches negative infinity, which is quite obvious. So from here we can say clearly that f of x approaches positive, negative infinity. Negative, sorry, negative infinity. It approaches negative infinity. Okay, fine. Now let's approach. Now if you approach a2 minus. Now why a2 minus? Because in the interval a1 and a2, you need to approach a2 from this side. So this is basically negative. Similar case, you can observe that this expression is the main thing that we need to deal with. That is a2 minus x. Since x is less than a2, then we can say that this entire entity is greater than 0 and it diverges to positive infinity. Okay, cool. So we can see that the function f of x is actually continuous in the interval a1 and a2. But note that if we approach a1, then we see that the f of x function actually diverges to negative infinity, and if we approach a2, the function diverges to positive infinity. So what does it mean? Just a second. So what does it mean? This is the point where we use intermediate value theorem. Just a second. What is wrong with me? Okay. Say in this particular interval, oh, I'm sorry, why I just change the color? Okay. Now observe that if we have a1 here and a2 here, at a1 the function actually diverges to infinity, and there's something, and we see that this approaching positive infinity. At a1 it is something negative, and at a2 it is something positive. So we can clearly see that since the function is continuous, it must intersect the x-axis at some point. So this is actually called the intermediate value theorem. So by using the concept of intermediate value theorem, we can clearly understand that this function has roots, or f of x has real roots in every ai plus 1 interval. And in every ai plus 1 interval, this function has a root. Okay, so how many intervals can we frame in like this? We have a1, a2, we then have a2, a3, all the way to an plus 1. So there are basically n minus 1 roots. But we are told that this function has n real roots. This function must have n real roots. This function must have n real roots. So where does this extra root come from? From where can we get this extra root? Okay, so let's see one thing. What if we f of 0. If we plug in f of 0, we'll have n minus 2015. Now there can be two situations. One situation is that n is actually greater than 2015, and the second case is n is less than 2015. Okay, cool. Taking the first case, if n is greater than 2015, then we can clearly say that this thing is positive, that is greater than 0. And note that if we take limit n tends to negative infinity, what do we get? Let's have a look. Here we can see that the entire x term is actually in the denominator. So if we approach x to negative infinity, this entire term approaches 0. Similarly, this term approaches 0. So the entire thing actually approaches 0. This entire thing actually approaches to 0, which means that this function approaches to minus 2015 as x approaches to negative infinity. Now we can apply our IVT again. At 0, so this approaches minus 2015. At 0 we have something positive, and at negative infinity we have something negative. Now we can clearly understand that this particular function is continuous in the field 0 to minus infinity to 0, because there are no point of discontinuity as defined by the function. So you can clearly see that from here we get the last root. So we get another root. Okay, so this completes our n roots. Now the second case is, what if n is less than 2015? Then this thing will be negative, and at the same as previous, we can now approach n to positive infinity, and we will note that if we approach to positive infinity, what do we get? Actually doesn't matter. No, it doesn't matter. It doesn't matter. If n is actually approaching to infinity, just a second. If we take n as, okay, let me see. Say we take limit of x approaching to infinity, then we get this thing is equal to, yes, exactly, this minus 2015 again. Okay, got the point. Take the limit x approaching a1 from the left hand side, then obviously f of x will be approaching to, just a second, let me see. We have this function, if x approaches a1 from the left hand side, then this entire entity will diverge to positive infinity. So clearly f of x will be something positive. But we have assumed that this thing is actually less than 2015. It means that this thing will be negative. Right? But we know that this function is continuous in 0 to a1. So we can see at 0 we have something negative, and at a1, and if we approach a1 from the left hand side, then we get to something positive. Again by IVT we get the last root. So this probably completes our proof. If you have any solution, then you can please give me. If not in the live chat, then in the comment section you can give me. Actually, uh, yeah, you can give me, obviously. Okay. So I'll be waiting for 1 minute, then I will move on to the next question. Okay, let's move on. Okay, so this was our first question. You can have a look on the description box. I have put a link on link of all the questions in the description, and you can obviously check out my website. I in my a lot of questions, and I just recently started to publish a few questions over there. So if you want, then you can if you want some additional questions, then you can obviously visit my website. That is in my about section in the YouTube channel. If you go to the about page, then you can find a link to my website. I will also put the link of my website in my description, so you can check that out. Okay, so actually I have already published a question sheet on the pigeonhole principle. You can have a look on that particular particular question sheet, and I might upload a few more questions over there, a few more problem sheets, and you can obviously check them out. Okay, so now back to business. Let's just select this question. Okay, fine. So we are given that we are given a prime which is greater than 3. Obviously it's a prime which is greater than 3 is obviously odd, and we are given this sum. So if we add this, if we add all the terms, then this summation actually becomes to a by b, which is a rational form because ab has no common divisors in them. So we need to prove that a is divisible by p. So if you want to give a try, then you can give it. Okay, so let's try to solve this question. This is actually not a very difficult question, but we can approach it. It's actually a very beautiful question. I actually like it. It's a very simple question. It might seem a bit difficult, but it's a very simple question. So we have the summation. Just a second. So we have the summation from k equals 1 to p minus 1, 1 over k. Okay. So what is it actually? What is it actually? Note that it's 1 over 1, it's 1 over 2, plus it continues till 1 over p minus 1. Okay. So the thing we are going to do here is we will take this term. You can prove it by induction. It's a very simple thing that if 1 by n falls under this series, then 1 by p minus n will also fall under this series, which is pretty obvious to see because 1 is the least number and p minus 1 is the largest number. So if p minus 1 exists, then p 1 over 2 over here. So it is pretty easy to understand. So this thing is basically nothing but n times p minus n plus n, which is p times p over n times p minus n. Okay, cool. So how long do we need to carry on this process? Because we are just taking half of the terms. Now we obviously know that p since p is odd, then p minus 1 must be even. And if p minus 1 is even, then obviously we can halve the groups. So we just need to decrease the number of additions. So this thing turns out to be now basically nothing much. You can just plug out p, and this is n times p minus n. So if this thing is equal to a by b, then obviously p and a, or a must divide b. P must divide a. Just a second. P is a prime number, so yeah, p must divide a. So obviously p divides a. Okay. So this was the proof. This was kind of fun. This was a very interesting problem. It's a very simple one, but a very interesting one. Okay. I'll just take a few seconds break, and then we'll move on to the next question. Okay, cool. Okay, so let's move on. This is my second live stream. Yeah, this is my second one. Actually, I already had done a few test live streams. So probably I will do a few more live streams on problem solving like this because I love problem solving. It actually doesn't matter whether I'm able to solve it or not, but I just enjoy problem solving. Okay, never mind. Okay. So the next question is, I just took this particular question from a book, from a number theory book. I like this question and I just took it. Okay, so this question, we need to prove whether this particular function, whether this particular series is convergent or not. Okay. Okay. Uh, so we need to check for convergence. We need to check for convergence. So how do we check for convergence? We have a lot of tests, ranging from the p-series test, comparison test, the ratio test, the Cauchy integral test. So you can use any one of them. I don't know which one will work, but I actually use the Cauchy integral test, and I think it works by using Cauchy integral test. I think it works. I'm not sure because I had never used Cauchy integral test before this. I'm just using it. So I used it, and hopefully it is solving. Okay. So what we basically do here is, what is basic Cauchy integral test? Let me just give a basic introduction about a Cauchy integral test. What is wrong with you? So what is Cauchy integral test? It says that if we have a sequence defined as f of n, and if we want to sum it up ranging from n equal 1 to infinity, so this particular thing will converge if integral 1 to infinity f of x dx is something finite. So this is the Cauchy integral test, that if this particular series is convergent if the integral of f of x dx is finite. Okay. So what is f of n here? Let's have a look on this. See that the first term is 2 over 1 divided by p. So you can clearly see that here the f of n, just let me write over here, and f of n is n plus 1 over n to the power p. So obviously, because the summation is something like this, n plus 1 over n to the power p, where n is from n equals 1 to, okay, cool. Okay. So this thing will be convergent if the integral of x plus 1 over x to the power p dx from 1 to infinity is a finite number. Okay. So this is a very trivial integration. 1 to infinity x to the power 1 minus p plus x to the power of minus p dx. So this is x to the power of 2 minus p divided by 2 minus p plus x to the power of 1 minus p over 1 minus p Now this is the integral from 1 to infinity. Note that if we plug in infinity over here, so this thing, this powers must be less than 1 so that we can get something finite. Why? Because if power is something greater than 1, then this thing will obviously diverge to positive infinity and we will lose the significance of this test. So in order to make this particular thing finite, we must say that 2 minus p is less than 1 and 1 minus p must be less than 1 too. Okay. Now obviously p can't be equal to 2 or p can't be equal to 1, which is quite obvious because in a denominator we can't have zeros. Okay. So 2 minus p must be less than 1. Uh, is it less than 1 or less than 0? Yeah, it is less than 0. I'm very sorry. It is not less than 1, it is less than 0. It is less than 0. I'm very sorry. Because in the numerator, if we have something x to the power which is greater than 0, then obviously what is actually infinity root over of infinity? It's because the infinity square is infinity. Don't just take this infinity as some numbers. It is actually infinity means something really large. So by infinity I mean approaching infinity. We just can't plug in directly. We can't plug directly infinity in certain cases. So we just approach infinity. So we can see that infinity to power something positive is actually infinity itself. So yes. So this thing you can see that p must be greater than 2. So p must be greater than 2. Okay. Now from here we can, yeah, obviously this is also 0. So from here we get p is must be greater than 1. Obviously if p is greater than 2 then p must be greater than 1. So p must be greater than 1. So if p is greater than 1 then this particular sequence converges. Okay. Okay, cool. Please do rectify me if I am wrong anywhere. Okay. Just give me a few more seconds. Okay. So let's just come back. Okay. Okay. This question I just took. This question I just took from a book. Okay. So the next question is, wow, a big integral. Ah, okay. Okay, nice. Okay. So let's let's just start. Okay, so this is a very big integral. This looks so big. So we are given some options also. Let's see which option is satisfies. I actually didn't solve this integral. I just thought of a way, but I have not tried it. So let's try. So as we can see that the the lower limit and the upper limit are basically opposite of some opposite sides. So if something is like this, then we can try to use King's rule. What is King's rule? I'll just give a brief introduction. If we have something like this, then by King's rule, so this is what we call King's rule. Okay, so we can try this out. Let's try what we can see. Okay, just a second. Okay. So let's define this. Sorry. So let's just define this integral to be some I. Now note that I is basically equal to integral minus 2014 to 2014 dx over 1 plus 2014 plus minus 2014 is 0. So we'll have sine of minus x, and sine of minus x is minus sine of x, and since we have an odd power over there, so we can say that this is minus sine 2015 x plus root over 1 plus sine, thus 4030 is even, so the sign will not change in this case. Okay, now if we basically add these two terms, this integral and this integral, if we basically add them, let's see what happens. LHS will be 2 times I equal to integral minus 2014 to 2014. Okay, adding them will give us so if you see that if we add them, then the denominator will get multiplied, and if we have it multiplied, then it will look something like 1 plus root over of 1 plus sine 1 plus sine 4030 x square minus sine of 2015 square, that is 4030 x. Now what shall be in the numerator? In the numerator we'll have this thing plus this thing. So if we add both the terms, we will see that this sine 2015, this sine 2015, sine to the power 2000, sine of x to the power 2015 will basically get cancelled out, because signs are actually uh, opposite here. Like it is plus over here and we have minus over here. Okay, cool. So we will have 2 times 1 plus root over 1 plus sine to the power of 4030x. So now if we solve the, if we just solve the denominator, then it will be 2002 to the power 2 times 1 plus root over 1 plus sine 4030 x over 1 plus 1 a square plus b square, a square plus b square plus 2 times ab minus sine to the power of 4030 x. Okay, so this basically means minus 2014 to 2014, 2 times 1 plus root over 1 plus sine to the power of 4030 x over, so this thing and this thing will get cancelled out. You can take 2, this is equal to 2, you can just basically take 2 common out from here. We'll have 1 plus root over 1 plus sine 4030 dx. Now these are basically the same things, so we just cancel out this. So finally we will have integral minus 2014 to 2014 dx. This is x minus 2014 to 2014. So this is 2014 plus 2014, 4028, and we know that 2 times I is 4028, so I is 2014. So do we have an option there? Yes, we have it. So this is the correct option. Okay, so nice one. Give me a few more seconds, please. This question I took from another book for JEE Advanced. Although it doesn't look like a JEE Advanced problem, this is just an easy JEE Mains problem. J-means often does these things, like they just give a big integral which might seem humongous and might cause panic attack for students. But these things are actually very simple if we just try to approach it. That's actually the beauty of J-means. The questions might seem heavily difficult, but they are quite easy. Okay, so this is the next question. Just give me a few more give me a few seconds. I'll just have a bit of water. Give me a few seconds. Okay, let's get back to work. Uh, okay. Okay, so this is a question of series. Okay. So we had given this thing. So we are given what is wrong with this pen. So let me write down this particular expression first. We have r over 1 minus 3r square plus r to the power 4. Okay. So do you think that this particular thing, this particular expression is interesting? Yes, whenever we have this kind of expressions where we have a bunch of things in the denominator and a few things in the numerator, the thing that we often do is factorize it and try to form a telescoping series. Okay, so let's try to do the same here. Here the telescoping series seems actually is quite visible. Oftentimes we see that the telescoping series, that a fraction does contain such identities which is pretty difficult to factorize. So it is pretty easy to factorize, as we can see over here. We can just set the things like this. Okay, now it is pretty simple to factorize because this is basically equal to r over this thing is r square minus 1 whole square minus r square. This is equal to r over r square minus 1 plus r times r square minus 1 minus r. So this can be basically written as r square minus 1 plus r minus r square minus 1 minus r. Note that we are getting 2r in the denominator, in the numerator. So we can basically divide it by 2, and we will see that this is r square minus 1 plus r times r square minus 1 minus r. So if we apply summation on this, what we will have, half times summation 1 over r square minus 1 minus r minus 1 over r square minus 1 plus r. Okay, so let's do a bit more factorization. One over, we can take r common from here, so we'll have r times r minus 1 minus 1 minus 1 over r times r plus 1 minus 1. Okay, so can we form telescoping series from here? Well, I'm not sure. Let's see. Now obviously r ranges from 1 to 10, so let's see. Okay, so let's see what we have. 1 over for the first case this will be minus 1 because this thing is 0, minus 1 over 2 minus 1, that is 1. Okay, fine. What else? Plus, if you plug in 2 over there, you will have 1 over 2 minus 1, that is 1, plus 1 over 6 minus 1, that is 5, plus if you plug in 3, we will have 1 over 6 minus 1, because r equals 3 and 3 minus 1 is 2, r equals 3 and r minus 1 is 2, 3 times 2 is 6, 6 minus 1 is 5. Oh, I'm sorry, I'm really sorry, it is minus. Minus. If you plug r equals 3, then we will have 3 times 4, that is 12. 12 minus 1 is 11. Plus, if you plug r equals 4, then we will have 1 over 11 minus 1 over 4. 4 times 4 plus 1 is 5, is 20, it is 19. So it's pretty easy to understand. We get some sequence. So let's just frame the sequence like this. We have minus 1, minus 1, plus 1, plus 1, minus 1 by 5, minus 1 by 5, plus 1 by 11, minus 1 by 11, oh, I'm really sorry, this is plus this is plus, and this is minus. And this is plus, this is minus. So this continues. So you can see that these things actually cancel out like this. So by carrying on this process, we see that the first and the last term basically remains. So first term is this, and what is the last term? Obviously, when we plug in r equals 10, when we plug r equals 10 over here, we get the last term. So if we plug r equals 10, then we will have 110 minus 1, because r is 10 and r plus 1 is 11, so it's 110 minus 1, that is 109. And obviously this will be minus. So do we have a minus thing? I don't think so. Yeah, we have minus. So what is this basically? 109 plus 1 over 109, 110 over 109, and we have 1/2 over here. If you remember, we have 1/2 over here. So if we multiply that half with the final term, if we multiply half with this, then this will be 55. This minus sign is obviously there, so it is something minus 55 over 109. Okay, cool. Okay, so this is the correct answer. Okay, give me a few more seconds. We're almost done, I guess. Yeah, this one and this one. Two questions remaining. Okay, so what we have here? We are given a sum. So this is not a sum. We are just given an expression which says that f and x is basically a series of x. Now these are not multiplied. We see that these are n digit number. So how can we deal with this? Note that before moving on to the question, we can obviously see that how we can deal with this. It's basically a sequence of x which continues. So this means that it is something of this form. Since there are n x's, so we can say that it is 10 to the power of n minus 1 x, or just a second, two-digit number means, yeah, fine, plus, we can see that 10 is a two-digit number which is actually 10 to the power 1. 10 to the power of n minus 2 x plus this thing will continue 10x. So we can basically take out x common from here. We can take x common out from here, and we will have 10 to the power of n minus 1 plus 10 to the power of n minus 2 this thing will continue till 1. This is a geometric sequence, and we know that what is the sum of a geometric sequence. So there are basically n terms starting from 1 to n minus 1. So there are basically n terms. So since 1, we can just assume that 1 is the first term. So 1 times 10 to the power. Since we are just multiplying 10 and we are getting this, so 10 is a common ratio here. Something of this one. 10 minus 1 is 9. So this is what f and x is. Okay. This is what f and x is. Now we need to deal with this and this. fn3. So what is fn3? Let's see. fn3. In place of x, we just plug in 3. So this is fn3. And what is fn2? It's 2 times 10 to the power of n minus 1 by 9. Okay. So we are told that we need to square this. So we are told that we need to square this term. Okay, so let's do it. Square and add them. Okay. So let's square this. So if we square this, then we will have 9 times 10 to the power of n minus 1 over 9 squared plus 2 times 10 to the power of n minus 1 over 9. So we can just take 10 to the power of n minus 1 over 9 common out from here. We will have 9 times 10 to the power of n minus 1 over 9 plus 2. Okay. So this and this gets cancelled. And we have 10 to the power of n minus 1 over 9 times 10 to the power of n minus 1 plus 2 plus 1, which is 10 to the power of 2n minus 1, a plus b minus a times a minus b. So what is this actually? This is nothing but 1 plus 10 plus 100 plus dot dot up to 10 to the power of 2n minus 1, right? So what is this? Note that we have defined f and x as this thing. If we plug in x equals 1 and n equals 2n, what do we get? We get 10 to the power of 2n minus 1 over 9. And that's it. We have our expression. This is basically the same expression. So this is nothing but f2n of 1. So the correct answer is C. Okay. So we are almost done. The last question remains. Okay, I've used 50% of my daily data. Let me just finish the stuff as fast as possible. Okay, so this is the last question for today. Okay, cool. So this question, I remember this is a question of RM. Don't ask me which word I didn't remember. I don't remember. I don't remember which year. I just got a question of RM and I'm just doing it. Okay. So we need to find the natural number solutions for x, y, and z for this. Okay. So let's just expand the things. What we get? 2 to the power of x plus y minus 2 to the power x minus 2 to the power of y plus 1 equal to 2 to the power of 2 to the power of z plus 1. So here plus 1 and plus 1 gets cancelled. So we have 2 to the power of x plus y minus 2 to the power of x minus 2 to the power of y equals 2 to the power of 2 to the power of z. Okay. So note one thing. We can just take the minus signs on that sides. Okay. So note one thing. If we add something with 2's power and we expect to get a 2's power back, so what does it mean? So there's only one thing that's possible, that is this entity is equal to some 2 to the power of n times 2 to the power of 2 to the power of z, because that is the only case where if we add two multiples of two powers of 2 and we get a power of 2 as a result. This is the only possible case. You can just understand it, because if we add something with this and this, then we will get something, and we know that if 2 to the power of x divides 2 to the power of y, then x is less than y. If x is less than y, then this thing always holds. So applying the same idea, we can clearly say that 2 to the power of x plus 2 to the power of y must be of the form 2 to the power of n times 2 to the power of 2 to the power of z. Now note that this thing is again up 2's power. So when do we get this? So basically we need to deal with this. When do we get 2 to the power of a plus 2 to the power of b equals 2 to the power of c? When is it possible? Clearly we can see that c is greater than both a and b. So we can just assume that say a is less than b. Now we know this. We know this thing. We know this thing. Now a is minimum here, minimum among a, b and c. So what we can do is basically divide both the sides by a, 2 to the power of a. Okay, so this thing, from here we can understand that this is only possible, possible only, this is possible only if b equals a and c equals a plus 1. Because if you add 1 with an even number, you can't get an even number. This only possibility is that this is an odd number and this is an even number. So it holds only if b equals a and c equals a plus 1. So we can understand that this thing is possible only if x equals to y. Okay? So if x equals y, what do we get? Again, the same thing. X plus y equals 2 to the power of 2 to the power of z plus 2 to the power of x plus 1. Again, basically the same idea. 2 to the power of z is equal to x plus 1, and this is possible. When is it possible? And the second thing is that x plus y is x plus 2, so we can basically cancel this out. I think it's fine. Yes, it's fine. So we get y equals 2. So if y equals 2, then x equals 2. And if x equals 2 and y equals 2, what do we have? If x equals 2 and y equals 2, we have 2 to the power of 2 plus 2, that is 4, minus 2 square is 4, so this is basically 8, and this is 16 minus 8, which is basically 8. Okay, did I do a mistake anywhere? Just a second. No, I guess. We'll just assume that x is equal, so we just got that x is equal to 2. Now if x equals to 2, then x plus 1 equals to 3. And 2 to the power of z equals to 3 has no natural number solution. We have basically no solution for this. No natural number solution for this equation. No natural solution. As far as I think, I think it is true. Okay. Yes, obviously. There is no other way. Okay, so let me stop here because I've used 90% of my daily data. Okay, thank you so much. Let me stop the stream.